In this video, we will discuss 4 different measures of central dispersion. We have range, variance, standard deviation, and coefficient of variation. Another recall topic would be measures of dispersion. So this has been discussed during your biostatistics as well. So dispersion means it is a state of getting dispersed or spread out or scatter. So that means we are measuring the numerical values if they are together or if they are scattered to one another. In statistical dispersion, it describes how similar a set is to each other. So in other words, we would be able to see if the data is squeezed in together or if they are scattered from the mean. General characteristics: the lower the measure of dispersions, that means the more similar the values are, because when there is a very low dispersion, that means they are not scattered. That means the values are very similar to each other. On the other hand, if there is a higher value for the measure of dispersion, this means that the values are not similar with each other. In general, the more spread out a distribution is, that means the larger the measure of dispersion. The different measures of dispersion would now be range, coefficient of variation, standard deviation, and variance. We will discuss these one by one. Range is the most common type of measure of dispersion. This is easily understandable because it is the simplest form of measurement of dispersion. This may simply be computed by the difference between the two extreme observations of the set, which are these two extremes, the lowest and the highest value. So simply, this is the difference between the maximum value and the minimum value given in a data set. So for example, we have 1, 3, 5, 6, and 7. To compute for the range, we just have to get the difference of the highest and the lowest. So 7 minus 1 equals 6. So that means there is about 6 numbers away from the 7 and the 1. This is now the range. This is based on two extreme observations only. That's why it is not reliable, because it only depends on these two variables. That means it may also be affected by fluctuations. Our second measure of dispersion is variance. So when we say variance, this is the deviation of all values from the mean. So mean and variance are interrelated with each other. A simple definition would mean the estimate of how far the number is from the mean value. How far or how the data points differ from the mean, or it's the distance of the different data from the mean. So how do we get the variance? We just have to compute for the average of the squared differences from the mean. As we have mentioned earlier, the variance and mean are interrelated. So here we have the purple circle. So these are your data, and the orange line would be your mean. So in variance, we are trying to see the distance of the different values from the mean itself. So how far away are the values from the mean? Let's now compute for the variance. So the formula that we have mentioned earlier is the average of the squared differences of the mean. So we have several steps to follow. First, of course, is we have to find the mean. So add all the values. Let's use simple values first. We have 5, 10, 15, and 20. So when we add them up and divide them into how many numbers there are, we will get the mean. So all of these numbers added divided by 4, we have 12.5. So that is now our mean. Next step would be to subtract the mean from each value. So that would be our second column. So x minus the mean. So for example, on the first number, 5 minus 12.5, we will get negative 7.5. So we do this on all the numbers. So 10 minus the mean, 15 minus the mean, 20 minus the mean. After we do that, we create a third column so that we can square each of the results. So we call these as the squared difference. So on the second column, we have negative 7.5. We square that. So negative 7.5 times negative 7.5 will have 56.25, and then we do it again to the rest of the numbers. And the last step is to get the average of the squared difference. So we add all the numbers on our third column. We divide it into how many numbers we have, and then we will have our variance. So that is our last step. First, we have to compute for the mean, and then we have to subtract the mean from the values, and then square the differences, and then we have to get the average from the squared differences. So that is now our variance formula. So our variance here is 31.25, so that means the values are 31.25 far away from the mean. Now if the variance is 0, that means the data is identical. The more the variance, or the higher the variance, the more the values are spread out, and the lesser the variance, the lesser the values are spread out as well. Since this is a measure of dispersion, the general rule applies. The higher the value, the higher the dispersion. So in this case, the higher the variance, the higher the dispersion, or the spread out the values are, and the lower the variance, the lower the values are spread out. But there is a small change if the data we have is considered a sample data. In statistics, it is very important to distinguish between a population and a sample data. A population is defined as all the members of interest. So for example, we want to test diabetic patients. That means all the test results of diabetic patients should be included in the test. So population is the whole group. A sample is only a part of the population. So in this example, if we want to test diabetic patients but we were only able to include diabetic patients in one hospital, then our data becomes a sample data. So a sample data is never the whole population. This is the selection taken from a identified population. Now, this is the formula for the variance. This is the average of the squared differences from the mean. So the numerator is the squared differences. So this is all the numbers after you square it. So you add them up and then you divide them by the denominator, which is the number or the amount of numbers, and then you'll get the average. So that's the average of the squared differences of the mean. That is the formula for variance. Now, if the data is considered a sample, we now have to make a slight adjustment at the denominator. So please refer to the formula at the bottom. The adjustment we have to do is to subtract 1 from the population, which is n. So it would now be n minus 1. So what is the purpose of doing this? The purpose of this little difference is to get a better and an unbiased estimate of the population variance. So this is by dividing the sample size lowered by 1. We can compensate for the fact that we are working only with a sample rather than the whole population. Given this new information, let's now adjust our variance, considering that our values are only sample data and not population data. So everything will still be the same. It's just that we need to change the denominator into a lower value so that we can adjust for the population being smaller. So instead of using 4 as a denominator, we have to subtract 1. So 4 minus 1, we will now have 41.67 as our new sample variance. The third measure of dispersion is the standard deviation. SD would give the measurement of how spread out the numbers are. The symbol is the Greek letter for sigma. The formula is the square root of the variance. So you would have to compute for the variance first before you can get the standard deviation. When you have the variance, simply get the square root of your variance result, and that would be your SD. SD is also the most frequently used measurement of variation. This is the formula for standard deviation. So first we have to get the variance. So in here, we used the formula for sample data because mostly the data that we are able to collect are sample data. It is very rare that a complete population is tested. So let's stick with n-1 for the variance. And then we simply get the answer here and get the square root of the variance. And that would be our standard deviation. Notice the symbol for variance, it's sigma squared. And for standard deviation, it is just the sigma sign. let's go back to the data that we have earlier. So we have already computed for the variance. For population, it's 31.25, and for sample, it's 41.67. So for the population data, we get the square root of the variance, 31.25. We now have 5.59, so that is the standard deviation. For the sample data, we get the square root of 41.67, and now we have 6.45 standard deviation. So just to give a different perspective about standard deviation, in this picture, we are given the different depths at different locations of a river. So we have all these numbers. There's 0.5 depth, 6, 10, 5, 8. Well, the first thing we need to do when we compute for the standard deviation is to find the mean, because we need the mean for the variance. So the mean for this is 4. So this is the mean depth of the river. After that, we compute for the variance. And then after we get the variance, we get the square root of the variance, and we will get the standard deviation. So again, we are showing the mean of 4, and our standard deviation after square root is 3.55. So what does this mean? This means that the typical depth of the sample varies from the average depth of 3.55. So we now have a standard depth. That's why it's called a standard deviation. So this means that the normal interval of the river depths would be 3.55. Again, 3.55 is the standard depth, which refers to the normal depth. So if the value is less than 3.55, that means it's not deep. But if the value is more than 3.55, it may mean that the depth is deep. So 0.5 is shallow and 10 would be deep. The last measurement of dispersion is coefficient of variation. So this gives a percentile expression of the mean. This is an index of precision. So the formula would be the standard deviation divided by the mean multiplied to 100. So this is used to compare variances of different sets. So for example, we have different sets of numbers, and then they have different variances, and we would want to compare these two sets to each other. We can use the coefficient of variation. For interpretation, when we get the coefficient of variation, the higher the CV, that means there is a higher in variation. They are directly proportional. But for chemistry, the CV of highly precise analyzers can be lower than 1. So the lower the CV, the better, because that means the more precise the analyzers are. So let's give an example. For example, we have two machines. So one uses the hexokinase method, and then the other one uses the glucose oxidase method, and we want to see how they differ with each other. The standard deviation of the first one is 4.8, while the SD of the second one is 4.0. So they have different SDs. The mean is 120 on the first one, and on the second one is only 100. So the results are also different. But now we want to see which method is more precise. As we have mentioned earlier in the previous slide, CV is an index of precision. So we can use this computation to see which between these two analyzers is more precise. So we now compute for the CV of each. How do we compute for the CV again? It's the standard deviation divided by the mean multiplied to 100. So which one is more precise? After computing for the coefficient of variation of each analyzers, the first one gave a CV of 0.04%, and the second one also gave a coefficient of variation of 0.04%. So which method is more precise now? With the coefficient of variation being the same, it means that there is no method more precise than the other, because they have the same performance in terms of precision. So that is how we use coefficient of variation. And that sums up the discussion about the measurements of central dispersion. Please like the video, subscribe to the channel, and watch the other videos. Thank you for watching.